Hello everyone, and welcome back to TeachAstronomy. My name's Victoria, but you can call me Vicky. And I just realized the door is open behind me, but it's okay because no one's going to be coming in the door. How are you guys doing today? Happy Monday. Today is the last day of Bookstream for Dreams of Other Worlds. And the last day of Bookstream for a little while because we're switching gears after we chat with Professor Impey about this one and doing some other stuff. Hello, Lynn Jersey. How you doing? I was late because I had an orthodontist appointment. Got a piece of metal removed from my mouth after having it in my mouth for 10 years, and I had like a permanent retainer on the back of my teeth, and now it's crazy because like it feels so smooth, and there's been metal in my mouth for the last 10 years, and it's gone now, and it's very weird, but I'm very excited. Anyway, got my tea brewing. Smells good. And I've got the book here, and let's just conclude Dreams of Other Worlds. So this chapter isn't super long because it is just a conclusion, but it's looking forward. Also keep in mind this book, especially for this chapter, this book was written in the early 2010s. I think it was published in, let me check, 2013. So a lot of stuff like New Horizons is mentioned. New Horizons hadn't gotten to Pluto yet, and a lot of other missions that have obviously, had a lot more happening since this book was written. So it might be a little bit dated, but still very good. So, all right. New Horizons, New Worlds. At the beginning of this book, we encountered the Greek philosophers who let their imaginations roam beyond the visible, everyday world. One was Democritus, who was 40 years younger than Anaxagoras. Apparently, they knew each other. Democritus was known as the laughing philosopher for his habit of seeing the lighter side of life and mocking human frailties. He developed an original idea of Lepicus into the atomic theory. According to Democritus, the physical world was made of microscopic, indivisible entities called atoms. The atoms were in constant motion, and they could take up an infinite number of different arrangements. Sensory attributes like hot, smooth, bitter, and acrid emerged from assemblages of atoms, but were not properties of the atoms themselves. It's a strikingly modern view of matter. By analogy, a beach looks smooth from a distance, but close up we see it's actually composed of particles ranging from tiny sand grains to pebbles and boulders. Democritus speculated in a similar way about the Milky Way, where its smoothness conceals the fact that it is composed of the combined light of myriad stars. Several centuries later, Archytas, all these names that we brought up in the beginning of the book, that was like 3 months ago. Several centuries later, Archytas made a logical argument that there was a space beyond the whirling crystalline spheres. Arriving at the edge of heaven, he imagined, and extending your arm or a staff, either it meets resistance and a physical boundary, or it extends beyond the edge. If the universe is contained, it must be contained within something larger. If we can reach beyond the edge, we define a new edge, and that must continue without limit. In this way, he argued that space must be infinite. The Greek imagination leapt downward to the invisibly small and upward to the unknowably large. By the late 20th century, scientists knew that the span of scales from the size of a proton to the size of the observable universe was 42 powers of 10. Human imagination, however, is not so neatly bounded. We can easily imagine what is, a phenomenon that's allowed by the laws of nature, as well as what isn't, a phenomenon that violates laws of physics as we know them. There's even a third, limbic category, a situation that doesn't violate any laws of nature, but which doesn't occur in our universe. In the early 21st century, scientists are once again pushing the boundaries of physical explanation, small and large. So particle theorists dream of 9-dimensional vibrating strings deep within every subatomic particle, worlds within the worlds. And cosmologists dream of an ensemble of spacetimes with wildly different properties, of which our universe is just one example, worlds beyond the world. On Earth, the horizon is the farthest you can see because of the curvature of the surface of the planet. The distance is surprisingly small. Standing in a small boat on a large body of water, you can only see 3 miles in any direction. Sailors in antiquity were familiar with the slow disappearance of a ship as it sailed away, until only the tip of the mast was visible. This led them to speculate and search for exotic lands that might lie beyond the horizon. Astronomy also has the concept of a horizon as a limit to our view or to our knowledge. The event horizon emerges from the general theory of relativity. Einstein's formulation of gravity is geometric. Instead of the linear and absolute space and time of Newton's theory, Einstein made an explicit connection between space and time and posited that mass curves space. I just remembered that I have tea brewing and I don't want to oversteep it, so I'm just gonna... It's black tea, so you can oversteep it very quickly. I used to work at a tea shop. This is the only reason I know these things. Yeah, you love New Horizons. Yeah. New Horizons is doing great. Anyway. Where was I? Okay. A compact enough object will distort space-time sufficiently to form a black hole, and the event horizon is the surface that seals a black hole off from the rest of the universe. It's not a physical barrier. Rather, it's an information membrane. Radiation and matter can pass inward, but not outward. Black holes are enigmatic because the region inside the event horizon lies beyond the scrutiny of observations. Cosmology has its own version of this idea, which is complicated by the expansion of the universe. The particle horizon for the universe divides events into those we can or can't see at the present time. The universe had an origin, so there are regions from which light has not had time to reach us in the 13.8 billion years since the Big Bang. If we're patient, light from ever more distant regions will reach us, so the observable universe grows with time. Meanwhile, the event horizon of the universe is the boundary between events that are visible at some time or another and events that aren't visible at any time. Standard Big Bang cosmology predicts the existence of space-time beyond our horizon, possibly containing many star systems in addition to the 10 to the 23rd visible through our telescopes. There are many worlds beyond view, perhaps more than we can imagine. I'm just going to take a sip of tea. Am I going to burn myself? Probably. Let's find out. Some fun tea ASMR. No, I'm not going to do it because I'm going to burn my tongue and then I'm not going to be able to taste anything. Okay. I'm going to keep going. Top of the morning to you, Ox Bowman. Thank you for joining us today. All right. Observational astronomy is a young activity. After tens of thousands of years of naked eye observing, the telescope is just 400 years old. Space astronomy is only 50 years into development, and the cost of launching a big glass into orbit means that the Hubble Space Telescope isn't even among the 50 largest optical telescopes. In what follows, we summarize what the future might hold for space science and astronomy, in terms of the missions recently launched or those on the near horizon, a few years from launch. The mid-horizon is 5 or 10 years from now, where the uncertain funding landscape and the high cost of missions make the view very indistinct. The far horizon can depend on technologies not yet developed or not yet perfected, and is beyond view. Any projection of more than a few decades is in the realm of speculation and imagination. To close this book, we consider 3 pairs of missions that promise to advance our knowledge of other worlds: 2 within the solar system, 2 looking at nearby stellar systems, and 2 studying the distant universe. The heir to Viking and the Mars Exploration Rovers is the Mars Science Laboratory, or MSL. Following the tradition they established with Spirit and Opportunity, NASA asked students to submit essays to give MSL a name. The winner from among over 9,000 entries was 6th grader Clara Ma, who wrote, "Curiosity is an everlasting flame that burns in everyone's mind. It makes me get out of bed in the morning and wonder what surprises life will throw at me that day." And so the most sophisticated robot ever built was named Curiosity. Clara Ma got to inscribe her name on the metallic skin of the rover before it was bundled up for launch. Over 1 million people worldwide are part of the mission in a smaller way, by having their names added digitally to a microchip on board. The public is clearly engaged in this Mars rover. In the months leading up to the launch, Curiosity had over 30,000 followers on Twitter. The Mars Science Laboratory is a mission with a high degree of difficulty. Technical problems forced it to slip from a launch window in 2009 to the next one in late 2011. And meanwhile, the budget ballooned to over $2.5 billion by the time of the launch on November 26, 2011. Choosing a single place to land on Mars and answer profound questions about the entire planet was difficult. Mission planners had a series of 5 workshops to whittle 60 possible sites down to 4, and then they let the decision float as long as they could until selecting Gale Crater. It's like playing roulette and betting the farm on a single number and a single spin of the wheel. The stakes are enormous. Imagine trying to identify a single place on Earth that would be representative of all terrestrial geology and biology. Site selection was made a lot easier by maps from the Mars Reconnaissance Orbiter that shows features and surface rocks as small as a sofa. It hinged on engineering and safety constraints, like having a navigable terrain and avoiding high latitudes where less energy is available to run the rover. Beyond that, the key landing site requirement was habitability, evidence for presence of surface water in the past. Curiosity confirmed its landing site, Gale Crater, was once a shallow freshwater lake bed. Pathfinder, which crawled over Mars in 1997, was little bigger than a child's radio-controlled toy car. Spirit and Opportunity were the size of golf carts. Curiosity is like a small SUV. It's 10 feet long, 9 feet wide, 7 feet tall, and it weighs a ton. With that large mass, NASA couldn't use the bouncing airbag landing method of previous rovers, where retro rockets slowed the lander and the payload sprouted airbags on all sides to protect it as it bounced to a lazy halt in the gentle Martian gravity. MSL used a procedure challenging enough to have flight engineers reaching for Tums when the spacecraft started its final maneuvers 150 million miles from Earth, with no real-time control possible. It steered through a series of S-shaped curves to lose speed, similar to those used by astronauts in landing the space shuttle. The target landing area is 12 miles across. That sounds large, but it's 5 times smaller than for any previous lander. A parachute slowed its descent for 3 minutes, then jettisoned its heat shield, leaving the rover exposed inside an aeroshell attached to a sky crane mechanism. Retro rockets on the upper rim of the aeroshell further slowed the descent, and then the aeroshell and parachute were jettisoned. At that point, the sky crane became the descent vehicle, with its own retro rockets guiding it toward the surface. About 100 meters above the surface, the sky crane slowed to a hover, and it lowered the rover to the surface on 3 cables and an electrical umbilical cord. The rover made a soft, wheels-down landing, and the connections were released, and several as a fallback if the release mechanism were to fail. The sky crane flew off to crash land at a safe distance. Landing was set for August 6, 2012. The rover then readied itself for 2 years of exploring the Red Planet. Whew. That was the plan. And the outcome? Everything worked flawlessly. All the scary outcomes and potential disasters were avoided, and the spacecraft touched down gently near the edge of Gale Crater on August 6, 2012. Hundreds of engineers cheered, and the millions who watched online shared the pride of the team in their technical feat. In fact, the landing worked so well that NASA has decided to use the technology again to launch another rover in 2020. Hey, we know about that one. With an entirely different set of scientific instruments on board. Sounds like a rover we know. Oh, it's still hot. I did oversteep it. Oh no. Maybe I'll get some honey for it later. All right. Curiosity has a science payload 5 times heavier than any previous Mars mission. There are 10 instruments. 8 have U.S. investigators, and 1 each comes from Russia and Spain. Curiosity has a titanium robotic arm with 2 joints at the shoulder, 1 at the elbow, and 2 at the wrist. The arm can extend 7 feet from the rover, and it's powerful enough to pulverize rocks while being delicate enough to drop an aspirin tablet into a thimble. The arm is versatile. It has a hand lens imager that can see details smaller than the width of a human hair. It has a spectrometer that can identify elements. It has a geologist's rock brush, and it has tools for scoping, sieving, and delivering rock and soil samples to instruments within the rover. A set of 3 instruments called Sample Analysis at Mars will analyze the atmosphere and samples collected by the arm, with an emphasis on the detection of organic molecules and isotopes that trace the history of water in the rocks. The arm will deliver samples to another instrument that uses X-ray spectroscopy and fluorescent methods to analyze the complex mixture of minerals in a typical rock or sample of soil. Engineers took instruments that would fill a living room on Earth and squeezed them into a space the size of a microwave oven on Curiosity. Sorry about that. Kept getting messages from people. They don't need me right now. Hello, ASMK. How you doing? You depend on GR in normal life. All right. Let's see, where were we? Film director James Cameron lobbied hard for a high-resolution 3D zoom camera to be included in the mission. The option for 3D imaging had been cut for budgetary reasons in 2007, but NASA was savvy enough to recognize a compelling public relations angle. So Cameron was appointed as a Mastcam co-investigator and informally as a public engagement co-investigator, and the option was reinstated. However, in early 2011, the idea was shelved because there wasn't enough time to fully test the cameras before launch. Curiosity lost the potential for cinematic 3D imaging with the director's eye, but retained its fixed focal length cameras, which should return crisp 3D images for the duration of the mission. The mast cameras will view Mars from eye level, giving the public a sense of roaming on a distant world themselves. Nearly compensating for the loss of Cameron cinematography is a high-tech instrument called ChemCam, which uses laser pulses to vaporize rocks at a distance of up to 7 meters. I didn't know this was a thing that existed. What? It then performs a chemical analysis of the vapor, returning results within seconds. A Star Wars capability like that will undoubtedly capture the public imagination. If Curiosity's landing site is likened to a crime scene where damage was caused by the action of water, Curiosity is trying to identify the culprit long after they've left the scene. It told us beyond any reasonable doubt that at least one part of this small, arid world was once wet and hospitable for life. Also, we know from the recent orbiter data that water periodically flows on the Martian surface. Curiosity is not designed to detect DNA or other essential biological molecules, and it can't look for fossils in the rocks it studies. Rather, it's designed to detect organic compounds and provide an inventory of life's essential elements: carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus. Viking's tantalizing verdict on life of "not proven" resonates among planetary scientists, so they're cautious in setting expectations for Curiosity, but the improvements will be dramatic. Unlike the Vikings, Curiosity explored a crater certain to have been wet in the past. It can roam widely for its samples. The Vikings could only gather soil in their arms could reach. Curiosity is doing analysis of the interiors of rocks, and it is extraordinarily sensitive, able to detect 1 part in a billion of organic compounds. It will test the hypothesis that perchlorate can mask the detection of organics. It will decide if low levels of Martian methane are more likely to be geological or biological in origin. It will even study the pattern of carbon atoms in any organic material it detects. Dominance of even or odd numbers of carbon atoms, as opposed to random mixtures of each, would be evidence of the repetitious subunits seen in biological assembly. Early results indicate that the Martian soil is chemically complex and potentially life-bearing. Sorry. Oh, it's still very hot. Okay. And then we'll have to wait. The middle horizon for solar system exploration is cloudy. As impressive as Curiosity is, there's only so much that can be learned from a small payload of instruments shipped to the Martian surface. If chunks of Mars could be brought back to Earth, they could be analyzed in exhaustive detail, molecule by molecule. So sample return has long been the holy grail of Mars exploration. Unfortunately, it will be difficult and expensive. The current plan is for 2 rovers to go to the same site on Mars and drill down as much as 6 feet for samples, then cache them in a sealed storage unit. Then a rocket would be required to boost the samples into Mars orbit, and finally a 3rd mission would ferry them to Earth. This is what Perseverance is doing. Perseverance is doing the first part, getting those samples. Just the first part of this procedure will cost at least $2.5 billion US, and we wouldn't have the samples in our hands until 2022 or even later. Well, that's pretty close now, actually. The alternative is equally exciting: a study of water worlds in the outer solar system. NASA and ESA combined forces to draw up plans for a flagship mission to interesting targets far from the Earth. There were 2 concepts: an orbiter to study the Jovian moons Europa and Ganymede, and another to study Saturn's moon Titan. After a shootout in 2009, it was announced that the Jupiter mission would go first. The Europa-Jupiter System mission, or Laplace, will launch no earlier than 2020 and would reach the Jovian system in 2028, and it will consist of 2 orbiters, one built by NASA to study Europa and Io, and another built by ESA to study Ganymede and Callisto. Just NASA's part of this project has a price tag of $4.7 billion US, so funding is not yet guaranteed. If all goes well, 420 years after Galileo first noted Jupiter's largest moons, they will be observed in unprecedented detail by robotic spacecraft. These missions could cement the idea that habitable worlds don't just include Earth-like planets, but also large moons of giant planets. Mars lies beyond the edge of the traditional habitable zone, where water can be liquid on the surface of a planet. The outer solar system planets are miniature versions of the Sun in chemical composition, and so uninteresting for potential biology. However, large moons like Europa and Ganymede are confirmed to have watery oceans under crusts of ice and rock. Tidal and geological heating provide a localized energy source, so all the ingredients for biology are there. NASA's orbiter will measure 3-dimensional distribution of ice and water on Europa, and determine whether the icy crust has compounds relevant to prebiotic chemistry. ESA's orbiter will do the same for the enigmatic moon Ganymede, the largest in the solar system. The biological real estate of the cosmos could easily be dominated by moons like these, languishing far from their stars' warming rays. And I want to look up, actually, the Laplace mission. I want to know where it's at now, because I don't know. There it is. I don't know what's up with it. I haven't heard anything about it. It was proposed. Japan was interested in contributing. Oh, okay. It seems like it was kind of usurped by Europa Clipper. So Europa Clipper is still happening, of course, and it looks like they kind of shifted their focus onto that instead of the whole thing. Oh, I don't know why my little thing didn't come up, but I saw that the lovely Jan just followed. Thank you so much for following. Welcome to the TeachAstronomy family. Normally there's like a little like thing, but or did it happen and I missed it? I'm not sure. You guys can tell me. I may or may not have my headphones plugged in incorrectly, so I might not be able to hear anything. But thank you for following. But yeah, Europa Clipper is supposed to be launched in October of 2024. But no promises. It's got a few years. But it seems like that has kind of replaced this mission that Professor Impey was talking about, which makes sense. Because I did not hear about the Europa-Jupiter system mission. So, all right. The second pair of missions is exploring new worlds farther from home. across swaths of the Milky Way galaxy. When the first planet beyond the solar system was first discovered in 1995, it marked the dramatic end of decades of searching and frustration. A planet like Jupiter reflects hundreds of millions of times less light than is emitted by its parent star, and from afar it will appear very close to the star, like a firefly lost in the floodlight's glare. Astronomers therefore used stealth to discover exoplanets. They monitored the spectra of stars, like the Sun, and looked for Doppler shifts in the spectra caused by giant planets tugging on the star. This method has been an unqualified success. The number of exoplanets doubles every 18 months, and more than 5,000 have been discovered. It's a major step in the continuing Copernican revolution. Planets form throughout the galaxy as a natural consequence of star formation. Timing is everything in science. It's often fruitless to be too far ahead of your time, but being slow to innovate means being left in the dust. Bill Barucki hit the sweet spot with his idea of a different way to find exoplanets. Working at NASA Ames Research Center, he realized that a planet transiting across its star would dim it slightly by an amount equal to the ratio of the area of the planet to the area of the star. It was a statistical method, since even if all stars had planets, only a small fraction of them would be oriented so that the planet passed in front of a star. He realized that with the stability of the space environment, it would be possible to not only detect the 1% dimming caused by a Jupiter transit, but to detect the 0.01% dimming of an Earth transit. This was the chance to find other worlds like ours in distant space. Barucki and his team pitched the project to NASA headquarters in 1992, but it was rejected as being technically too difficult. In 1994, they tried again, but this time it was rejected as being too expensive. In 1996, and then again in 1998, the proposal was rejected on technical grounds, even though lab work had been done on the proof of concept. By the time the project was finally given the go-ahead as a NASA Discovery class mission in 2001, exoplanets had been discovered, and the first transits had been detected from the ground. Persistence had paid off. Kepler was launched in March 2009, and almost immediately showed it had the sensitivity to detect Earths. It is using a 1-meter mirror to stare at about 150,000 stars in the direction of the Cygnus constellation. Designed to gather data for 3.5 years, or 3.5 years, as one might say, its mission was extended in early 2012 through 2016, which is long enough for it to succeed in its core mission, conducting a census of Earth-like planets transiting sun-like stars. Early in 2013, the Kepler team announced results from the first 2 years of data. The results were spectacular. Over 2,700 high-probability candidates, more than quadrupling the number of known exoplanets. Nearly 350 of these were similar to the Earth in size, and 54 were in the habitable zone of their stars, 10 of which were Earth-sized. The team projected that 15% of stars would host Earths, and 43% would host multiple planets. The estimated number of habitable worlds in the Milky Way is 100 million. The imagination struggles to contemplate what might exist on so many potentially living worlds. Kepler is looking at stars within a few hundred light years, our celestial background. Meanwhile, astronomers have their sights set on mapping larger swaths of our stellar system. Launched by the European Space Agency in late 2013, Gaia is the heir to Hipparcos, measuring all stars in the Milky Way down to a level 1 million times fainter than the naked eye can see. The heart of Gaia is a pair of telescopes and a 2-ton optical camera, feeding a focal plane tiled with over 100 electronic detectors. Kepler has a camera with 100 million pixels. Gaia's camera has 1 billion. Hipparcos studied 100,000 stars. Gaia will chart the positions, colors, and brightness levels of 1 billion stars. Not only that, it will measure each star 100 times, for a total of 100 billion observations. Like WMAP, Gaia is at the L2 Lagrange point, 1 million miles from Earth, gently spinning to scan the sky during its 5-year mission. The result will be a stereoscopic 3D map of our corner of the Milky Way galaxy. It is elegant. I don't know why my little My little notifications aren't working. That's weird. I think so far it's only been the lovely Jan that has followed and not gotten their little bidding. All right. Gaia will detect planets. Although that's not its primary objective, it will carry out a full census of Jupiters within 150 light years, not by looking for a Doppler shift or an eclipse of the parent star, but by actually seeing the star wobble as it is tugged to and fro by the planet. This is a truly minuscule effect. The sun wobbles around its edge due to the influence of Jupiter, but Gaia will be looking for a similar motion on stars hundreds of trillions of miles away. It's like trying to see a penny pirouetting about its edge on the surface of the moon. As many as 50,000 exoplanets may be discovered this way, compared to the current census of a few thousand candidates. Gaia will also detect tens of thousands of dark and warm worlds called brown dwarfs, which represent the twilight stage of stars, not massive enough to initiate nuclear fusion. It will also be able to detect dwarf planets, like Pluto, in the remote reaches of the solar system. Such planets are distinctive and interesting geological worlds in their own right. Gaia represents our coming of age in the Milky Way. It also provides a bridge to the last pair of missions we will consider, since the motions of the oldest stars in our galaxy were imparted at birth, so those motions represent a frozen record of how the galaxy formed. Current theories suggest that large galaxies were assembled from the mergers of smaller galaxies. Most of these mergers occurred billions of years ago, but traces remain in the form of streams of stars threading the halo of the galaxy like strands of spaghetti. This type of galactic archaeology is a vital part of understanding how the universe turned from a smooth and hot gas to a cold void sprinkled with island universes of stars. Cosmology is a vibrant field, spurred by the new observational capabilities, computer simulations, and increasingly tried and tested theories of gravity and the Big Bang origin of the universe. The mid-horizon in cosmology is defined by the James Webb Space Telescope. We all know how that went. Which is an ambitious successor to the Hubble Space Telescope. Hubble's mirror is 2.4 meters in diameter, limited by the size of payload the space shuttle could heft into a low Earth orbit. JWST will gather 7 times more light with its 6.5 meter mirror, even though it will be launched on an Ariane 5 rocket, which is a maximum payload diameter of 4 meters. This clever trick is accomplished by a design where the segments of the telescope unfold after it's deployed, like flower petals, adding greatly to the engineering challenge. JWST will also be located at L2, the increasingly crowded watering hole of many astrophysics missions. The telescope and its instruments will be too far away to be serviced by astronauts, so the stakes are high, and everyone involved in the project feels the pressure. JWST's cost has ballooned to over $8 billion. It's much higher than that now. And the launch date has slipped several times, with a current estimate of 2018. Nope. Although the project has broad support from the astronomical community, the high cost and repeated delays have brought it close to cancellation. NASA can only afford one flagship planetary science mission like MSL at a time, and it can only afford one flagship astronomy mission at a time. Until JWST is operating, no other big concept can get traction and a funding start. Astronomers struggle to maintain solidarity under such conditions. And there's a little picture here, and I totally forgot to get the pictures before this because, like I said, I was at the dentist. But this one's actually not too hard to see. So it's just comparing. So Hubble is the smaller mirror, and it's like a single. It's like a single mirror. Trying to do this all in reverse. Whereas JWST, it's got these like mirror panels. So once it gets up there, it's going to unfold. So that's how they're able to send it up on a rocket that normally accommodates smaller things than what it actually is. I wanna know what the price is, what the cost of JWST is now. Don't close. Let's find out. How much money is this telescope? Doesn't say. must say somewhere. How much money is it? Tell me the cost. Oh, okay, I found it. In October 2019, the total estimate for the project reached $10 billion. 10 billion US dollars. But even that is still like a year and a half ago now. So it's expensive. It's worth it, but it's pricey. Okay. Since JWST is a general purpose telescope, it will contribute to the study of exoplanets as well as the more remote universe. One of its instruments can take spectra of the feeble light reflected by a planet next to a remote star. By observing in the infrared, the exoplanet will be 10 to 20 times brighter relative to the star than it would be at visible wavelengths. Astronomers will take the most Earth-like planets and search for spectral features due to oxygen and ozone. These two gases are telltale indicators of life on Earth, and if they're seen in abundance in the atmospheres of exoplanets, it will be evidence of photosynthetic organisms elsewhere. The observations are extremely challenging, requiring 100 hours or more per target. But if they succeed, the detection of biomarkers will be a dramatic step in our quest to find a world like our own. However, the core mission of JWST is to detect first light. First light is the time in the youthful universe when gravity has had time to congeal the first structures from the rapidly expanding and cooling gas. The Big Bang was unimaginably hot, a cauldron intense enough to melt the four forces of nature into one superforce. By 400,000 years after the Big Bang, the temperature had dropped to 3,000 Kelvin, and the universe was glowing dull red as the fog lifted and the photons of the radiation from the Big Bang began to travel freely through space. The Dark Ages began. Theorists are not sure of the exact timing, but they think that it took another 100 million years or so for small variations in density to grow enough for pockets of gas to collapse. This would have been when the universe was at room temperature, 100 times smaller, and 1,000,000 times denser than it is today. At this point, the Dark Ages ended. It's likely that stars formed first and went through a number of cycles of birth and death before they agglomerated into galaxies. The first stars were probably massive, 80 to 100 times the mass of the Sun, and they died quickly and violently, leaving behind black holes. In this strange universe, no worlds like the Earth existed. The universe was made of hydrogen and helium. It would take generations of stars to live and die before enough heavy elements were created for planets and biology to be possible. Even JWST will probably not be able to detect the first stars, but it should be able to detect the first galaxies. Its superior capabilities are required because the Hubble Space Telescope has almost exhausted its light grasp as it looks for the first light. Less than 500 million years after the Big Bang, light travels so far and for so long to reach us that cosmic expansion stretches visible photons to near infrared wavelengths. Distant light slides off the red end of the spectrum and becomes invisible. In a sense, JWST is really looking for first heat. It is ambitious. The spatial vision would be different. Oh, because of the folding? Yeah, I mean, I'm sure they have I don't know the engineering and the optical science behind that, but I'm sure they have the way that they do the Giant Magellan Telescope, the GMT. It's being constructed in Chile. That's going to be 8 mirrors that all work together to be one giant mirror. So they have methods on how to do that kind of stuff and account for those things. If that's what you're talking about. I think that's what you're talking about. To take us beyond the horizon, we look to a mission that is currently taking data. Planck is the successor to WMAP, launched by the European Space Agency in 2009. It is a primary mirror about the size of a dining room table made of carbon fiber reinforced plastic coating. Carbon fiber reinforced plastic coating with a thin layer of aluminum, weighing only 28 pounds. The detectors are cooled to just above absolute zero. Planck improves on WMAP by a factor of 3 in angular resolution, a factor of 10 in wavelength coverage, and a factor of 10 in sensitivity. All of this means Planck will extract 15 times more information from the cosmic microwave background than WMAP. Nobody doubts the Big Bang anymore, so Planck is taking the theory to its limits, testing inflation, the notion that the universe underwent a phase of exponential expansion, an amazing 10 to the negative 35 seconds after the Big Bang. By making measurements with a precision of a millionth of a degree, the Planck mission may be able to determine how long inflation lasted and detect the signature of primordial gravitational waves imprinted on the microwaves. Or it may not provide any support for inflation, driving scientists back to the drawing board. If inflation occurred, quantum fluctuations from the dawn of time became the seeds for galaxy formation. If inflation occurred, there are regions of space and time far beyond the reach of our best telescopes. If inflation occurred, one quantum fluctuation grew to become the cold and old universe around us. The initial conditions of the Big Bang can accommodate many quantum fluctuations, each of which gives rise to a universe with randomly different physical properties. In most of those universes, the properties would be unlikely to support long-lived stars and the formation of heavy elements and life. Inflation therefore supports the multiverse concept, where there are myriad other universes with different properties, unobservable by us, and we happen to live in one of the rare universes hospitable for life and intelligent observers. In fact, the multiverse offers so many possibilities that everything that could possibly happen actually will happen somewhere. There might not just be clones of Earth beyond the horizon, but clones of us as well. Quantum genesis and the multiverse take us to a point where science becomes as wild and bold as any science fiction, a vision of worlds without end. And that is the end of the book. Yay! Woo! I should have balloons. We finished another one. That was great. What'd you guys think? Let's do a we finished so early. I'm gonna have some fun. We're gonna do a poll. I want to know, what was your favorite section? I know you can just type in the chat, but I feel like using the poll feature. Let's see, what were the best ones? I'm a little upset that they didn't mention that he didn't mention New Horizons. I feel like New Horizons is an important mission. And it was definitely on its way when he wrote the book, I think. Thank you for subscribing. My headphones definitely are in the wrong way. Because I couldn't hear that. But thank you so much for resubscribing, Lynn Jersey. You're wonderful. Thank you for being a part of the Teach Astronomy family and supporting us. Let's see. What was your favorite section? I feel like Dora. It didn't bling, did it? Okay, maybe they muted them? I'm very confused. I don't know what's going on. I suppose I don't really need to do a poll for this, but we're gonna put in WMAP and Hubble and Voyager, and the Blingerator is busted. It's very sad. Cassini and Spitzer, because apparently I only get I only get 5 spots. So you can vote for your favorite if you want. Just having a fun time. Oh, thank you so much, Lorraine. Blinged influence streaming sound. I hope you guys enjoyed it. But yeah, so now that we are finished with book number 2, even though Professor Impey has written a lot of other books, I think we are going to take a break from that and actually, I'm going to show you guys a little bit about the game that we're going to play. So So if you're new to Twitch, and if we brought you to Twitch, you might not know, or you may have figured out by now, that Twitch is generally a platform where a lot of people play video games and stream themselves playing video games. And we kind of are in the minority of doing like educational and science content, which we don't mind. We have a good time. Cassini's the winner. Thank you, one person, for voting. Congratulations. I was just having fun. But you know, a lot of people play games on here, and we're kind of in the minority. And I really like to play video games, and so does Michael, and Matthew plays some. And I figured, you know, why not play a video game? Because honestly, I really enjoy reading for you guys, but my throat is getting a little tired. Spitzer is really cool. Yeah, Spitzer Space Telescope is awesome. So I figured we're gonna try something new. It's the summer. We're gonna have a good time, and Worldhood. We're gonna play a space video game, which I don't know. Retro Space Station Builder. I'm gonna write that one down because that sounds interesting. But we're gonna start with Outer Wilds, which is a game made by. I actually don't know who it's made by. Mobius Digital and Annapurna Interactive, apparently. But let me show you guys some pictures of it. Hold on. Because it's a beautiful game all about exploring space, and I've never finished it. This is some of the art from it. It's gorgeous. And let me see if I can find like a trailer or something that we can watch. Oh. Is this a good trailer? I get an ad. Yeah, I think this is the right trailer. Okay. I'll show you guys. It's really pretty. I hope I don't get copyright struck for this. Oh no, can you not hear it? Oh, but the sound's so pretty. Shoot. Well, I don't think you can hear it right now, but there's a beautiful banjo song playing in the background. So you're essentially part of this, like, alien race that are not aliens in their, you know, solar system, that have taken the kind of steampunk approach to space travel and have decided, like, yeah, we can like build ourselves some spaceships. Let's do it. And they're going to like explore their solar system, and there's a lot of really cool stuff. There's a really interesting twist that I don't want to spoil for anyone, and I never finished the game, so I thought it'd be fun to play it with you guys. So yeah, we're gonna do that. I'm sorry you couldn't hear it because it's really epic. I will fix that for next time so you can hear it when we play, because the music's like half the fun. Banjo. Yeah, so it's an old game. It's from 2018, but we're gonna do it anyway because why not? Because I never finished it. Because, you know, I mean, we just read a book from 2013. We're not that current. Oh, you sent me the space station game? Project Space Station. Oh my gosh. It was for the Commodore 64. Oh my goodness. That looks really fun. I wonder if I can find an emulator to play that. That looks really cute. In this game, the player is put in control of NASA and tasked with building and maintaining a space station and generating enough money with commercial contracts to make up for an anemic yearly budget. That's really fun. You played on the DOS machine? Okay. Yeah, I'll look into that one. But yeah, so Bastions on Apple is good with sound. Okay. But yeah, so next week I'm going to try to get Chris on here to talk about the book. And then after that, we are going to play Outer Wilds. It's going to be fun. Oh, you get to fly the shuttle and do EVAs for building the ISS. Oh, that's awesome. That's so fun. But yeah. Well, you get to fly a spaceship in Outer Wilds too, and let me tell you, it's gonna be rough at first. That thing is hard to control, but it should be fun. There's like a lot of input that you guys can provide, and we'll have a good time. But yeah, I think I'm gonna wrap up here. So thank you guys all for hanging out. Thank you guys. A lot of you guys have been here for like the entire book, for the last book too. Thank you all so much for hanging out with me on Mondays and learning about space. As far as the rest of the week goes, on Wednesday we have our regular stream. Friday we had to cancel because Matthew is busy this week. He's actually on vacation, so we don't want to bother him, give him his time off. We will be here on Wednesday, and then also mark your calendars. July 2nd is our special special 1,000 follower celebration stream. So we're going to be streaming for like 3 hours, and we're going to be doing a bunch of different stuff. And there will be stuff that you guys can partake in. We're going to do a giant GeoGuessr game. I'm going to make like if you guys haven't played GeoGuessr, it's a game that you can lose a lot of hours to. It's essentially like Google Maps Street View, plops you down somewhere in the world and you have to figure out where you are. And it's online. And there's a way where you can invite people to play with you. And so I'm going to make some custom maps that'll be interesting, that are space related. And we can play those. We're going to have Matthew on and Michael and Chris, and just kind of going to have a good time. So make sure you're here for that. July 2nd, kicking off that holiday weekend if you're here in the U.S. And yeah. Lynn Jersey's very excited about you guys. All right, I think I will end it here. Thank you guys all so much again. Be sure to follow if you haven't already. Shout out again to the lovely Jan for following. And subscribe if you feel so inclined. Thank you again, Lynn Jersey, for resubscribing. 7 months. You get the 6-month badge as Jupiter, but yeah. We have different badges. I don't know if you guys ever noticed that, but the different badges are like different planets. They're very cute. But yeah, I will see you guys next time. Have a good rest of your day.